All right, today we're going to dive into a really fascinating mathematical framework that's all about helping computers make sense of a world that, well, isn't always neat and tidy. Let's get right into it. I mean, just think about it for a second. We live in this world full of nuance and gray areas, but computers, they love precision. They live on ones and zeros. So, what happens when the information we give them is messy? How do they even begin to navigate all that ambiguity? And this right here is the heart of the problem. Real world data is almost never perfect. It's usually got gaps, it might have contradictions, and it's often filled with vague ideas. For any system that's trying to learn or make a decision, that's a huge challenge. So, here's our game plan for this explainer. We're going to start by really digging into this world of uncertainty. Then we'll introduce a really powerful tool called rough set theory. After that, we'll look at the axioms, the rules that make it so reliable, see how it's grown over time, and finally, connect it all to how machines actually discover knowledge in the wild. Okay, first up, let's really set the stage. Let's explore this world of uncertainty and figure out why we so desperately need a new way to reason with information that's, well, imperfect. The data we're working with can be insufficient, right? Meaning we just don't have enough of it to get a clear picture. It can be inconsistent, where we have facts that actually contradict each other. It can be incomplete, full of missing values. And a lot of the time, we're trying to teach a computer about vague concepts, things like tall or hot, that don't have a sharp, crystal clear definition. This is the messy reality we have to deal with. So, how on earth do we handle this messy reality? That brings us to our solution, which is actually called rough set theory, or RST for short. So this was developed by a guy named Zdzisław Pawlak way back in the 1980s. And rough set theory is a tool designed specifically for this exact challenge. It gives us a formal way to work with uncertainty, not by trying to ignore it, but by actually embracing it and putting mathematical boundaries around it. Okay, this slide breaks down the core idea beautifully. Let's use a simple analogy. Imagine a park. That whole park is our universe. It's all the possible spots we could be. Now, let's say we want to define a vague idea, like the sunny area. Well, some spots are in direct, blinding sunlight. That's our lower approximation. They are definitely sunny, no question about it. Then you have other spots in the shade, some in partial shade, maybe near the edge of a tree's shadow. The entire area that could possibly be considered sunny, including all those partially shaded spots, that's our upper approximation. And this brings us to a really key distinction. The lower approximation, that's all about certainty. It's a very conservative, tight boundary with only the things that 100% belong. The upper approximation, on the other hand, is all about possibility. It's a much broader, more inclusive boundary that contains everything that might belong. And that space right in between those two boundaries, that's where the uncertainty lives. And rough set theory gives us the mathematical language to describe it. But, for a theory like this to be genuinely useful, it needs to have a rock-solid logical foundation. And that's where the incredible power of axioms comes into play. I mean, it's a fair question, right? How can we actually trust that these approximations are going to work consistently every single time? How do we know the whole system is logically sound and isn't just going to fall apart when we apply it to some new, tricky problem? Well, the answer, according to all the research, is through axioms. An axiomatic approach isn't just a part of the theory, it's considered the absolute foundation of it. Think of axioms as the fundamental rules of the game that we all agree on without needing proof, and from there, we can build the entire logical structure. So what do these axioms actually do for us? Well, for starters, they guarantee that the mathematical structures we need to even create those upper and lower approximations exist and are valid. They basically provide a logical rulebook, making sure the process is repeatable and consistent. And this creates a super solid base, not just for the original theory, but for all the amazing generalizations that have been built on top of it. And speaking of generalizations, let's take a look at how this solid foundation has allowed rough set theory to just grow and evolve over the last few decades. It's pretty cool. So it all kicked off in the 80s with Pawlak's original idea. Pretty soon after that, mathematicians took existing axioms, like Kuratowski's, and adapted them to give the theory its formal footing. And from there, it just exploded. Researchers started developing all these new generalizations to handle different kinds of data. And today, we're seeing it combined with other powerful tools like fuzzy set theory to tackle even more complex problems. And this just gives you a little taste of how versatile the theory has become. For instance, fuzzy rough sets are amazing for dealing with concepts that have degrees of truth, not just a simple yes or no, like how warm is it today? Other versions use different math structures, like lattices or neighborhood systems, to handle all sorts of different relationships in the data. But the key is, each one is built on that same axiomatic foundation, just tailored for a specific kind of uncertainty. Okay, so let's bring this all together. We've got this theory for handling uncertainty, and it's built on a solid axiomatic foundation. So how does this actually help a computer think or discover knowledge? Well, this leads us to this amazing concept called granular computing. Granular computing is a really powerful idea in AI. Instead of looking at every single tiny data point one by one, it groups similar or indistinguishable points into these things called granules. It's kind of like seeing a forest instead of trying to process a billion individual leaves. And it turns out, rough set theory is one of the most important tools we have for creating and analyzing these granules. And here's the payoff. By using these approximations, rough set theory can help a machine sift through a massive, messy dataset and find the features that actually matter. It helps figure out the smallest amount of information you need to classify something. This is absolutely crucial for things like recommendation engines trying to figure out what movie you might like, or for medical systems helping a doctor diagnose a disease from a whole mess of symptoms. It's how we find the signal in all the noise. So, as our world just keeps generating more and more data that's more complex, more messy, and more incomplete than ever before, the real question isn't whether we can get rid of uncertainty. We can't. The question is, how do we teach our machines to understand it, to reason with it, and ultimately to thrive in it? Tools like axiomatic rough set theory are a massive step in that direction, giving us the foundation we need to build smarter, more adaptable systems for the future. Thanks for joining me on this explainer.